Hello everyone, it's been a while since I posted a video, but here's this new integral I found, which has a pretty nice and interesting constant as a solution, and another usage of the O'Keneally technique on my channel, of which I hope to add to at a later date, but without further ado, let's get to it. Now, so the SI function. Okay, this SI function is the weird part here. This integral would be fairly easy, if not trivial, if it weren't for this. So the SI of x is defined as the integral from 0 to x, defines the Dirichlet integral, really. So then now our goal here is to expand it. So we know the Taylor series expansion for the sine is, okay, so the integral from 0 to x, we're going to have 1 over t times the sum, k equals 0 to infinity, minus 1 to the k, times t to the 2k plus 1, got an odd series, divided by 2k plus 1 factorial, dt. Okay, so just this t term and the 1 right here will cancel out, so that's nice. And then we just have to integrate term by term. So here's what we would get. So add 1 to the power of, or actually no, there is one more step. We have to interchange the sum and the integral, just swap it, right? Then we get the sum as k equals 0 to infinity. I'm going to factor out these parts of the sum as well, because they don't contribute to the integral at all. K plus 1 factorial times the integral from 0 to x, t to the 2k, dt. So now this is pretty trivial. You get add 1 to the exponent, and then divide by that new power. So then put in x, you get x to the 2k plus 1 divided by 2k plus 1. Put in 0, you get 0. So then all in all, we get the sum as k equals 0 to infinity for minus 1 to the k times x to the 2k plus 1 divided by 2k plus 1 times 2k plus 1 factorial. Okay, so this is a series expansion that we're going to use for the SI function. And so that's what we're going to O'Keneally in this. So let's cut to that right now. And we're back. So we can substitute here, we can substitute the SI function in the integral for this sum. So then we get the integral from 0 to infinity, e to the minus x divided by x. Or actually here, we're going to use this x term in the denominator to cancel out the odd part of the sum, or well, the fact that it's an odd. So this 1 will cancel out with the x in the denominator. Then we'll get this, k equals 0 to infinity. We'll have minus 1 to the k times x to the 2k divided by 2k plus 1 times 2k plus 1 factorial dx. Okay, so now you're at a bit of a crossroads. You could interchange the sum and the integral again, and then just integrate term by term, or you could apply the O'Keneally technique, both of which are valid and do lead to the correct answer. But since I feel the O'Keneally technique has a little bit more power, we're going to use that first. Okay, so here we're going to, right here we want an alternating even powered sum. So what sum is alternating and even powered? The cosine. Remember, the Taylor series expansion for the cosine of x is equal to the sum as k equals 0 to infinity minus x squared to the k divided by 2k factorial. So we have all these fundamental parts that we need for the integral inside of this new cosine sum. So all that we need to do to O'Keneally it further is to put an a right here inside the argument. Then you get integral from 0 to infinity e to the minus x times cosine of ax. So now this can be easily integrated with integration by parts. However, if you remember, the Laplace transform for the cosine of ax, or at, st is equal to s over a squared plus s squared, right? Now we're going to let s equal to 1. So we get back to here. So then we get this integral is equal to 1 over a squared plus 1. Good. And so now we have the equation set up so we can apply the O'Keneally technique. And I'll cut to that right now. Okay, so after substituting the series expansion of the cosine in for the cosine, we get this equation right here. And so now to apply the O'Keneally technique, we're going to let a equal to e here. So we're going to let a equal e, which is equal to e to the derivative, if you're new here. So now, put that in. We get the integral from 0 to infinity, 10 minus x times this sum, 0 to infinity. Okay, so you're going to have e to the 2k, right? We're going to have minus x squared to the k times e to the 2k, all over 2k factorial dx is equal to 1 over e squared plus 1. Okay, so now we're going to, if we're going to multiply both sides of the equation by a new function of 0, we're going to need this sum. We're going to need to be able to expand this series on the right-hand side, and we can. That's a simple power series. This power series is pretty simple. Just do minus e squared to the k. Okay, so now multiply both sides of the equation by f of 0, by a new function. Then we're going to remove this e. This e is going to transfer all of its power of k into this new function. It's going to make it f of 2k. Then same for this side, you just shove this new function of 0, f of 0. We're multiplying both sides of the equation by f of 0, by the way. I don't think I said that, but. So we're going to put this function of 0 inside the integral and inside the sum. So the big E here is going to operate on this function here. That's going to give us f of 2k. So now just erase that. And so now we have a new master theorem to plug in our new values of f of 2k into, to derive this integral up here. So here, just a simple transformation. I'm going to let f of 2k, so let f of 2k equal to f of k, all right? So I'm just going to turn the argument to f of k, because it's the same on both sides. So there. Okay, so now we have a formula to plug in our new values of f of k here, this new function on the index of the sum, into, right? So we're going to let f of k in our situation equal, so we have, or actually here, we're going to express this differently. So since, okay, you remember the factorial. The factorial, x factorial, is equal to x times x minus 1 times x minus 2, etc. All right? So now we're going to transform this into, when you get 2k plus 1 factorial, it's going to be equal to 2k plus 1 times 2k factorial, right? just plug that in there. So after plugging that in, we get 2k plus 1 squared times 2k factorial. And now, this is quite beautiful, you have the 2k factorial right there. So then you can just trivially let f of k equal to 1 over 2k plus 1 squared. Right? And so then you get this integral right here is actually equal to the sum is k equals 0 to infinity. You're going to have minus 1 to the k, alternating, and divide by 2k plus 1 factorial. K plus 1, or no, not factorial, sorry. 2k plus 1 squared. So this is famously equal to g, Catalan's constant, which is very nice. So, yeah. Of course, you could have avoided all this O'Keneally shit and just gone for the integrating term by term, of which I respect, but I feel like the O'Keneally technique can apply to more challenging integrals, and I'll make more videos on those more challenging integrals later on. So, hope you enjoyed this. See ya. That's it.